Hi, good afternoon. Welcome to the fourth session in the Spring 2024 SunokisisDC Digital Classics program. This semester is focused on digital approaches to cultural heritage, and in this session, this is the second of several sessions on various geographical or geospatial subjects. And we're talking this week about Geographic Information Systems, GIS, from maps to analysis. And we're extremely fortunate to have presenting with us, for us today, two experts on this topic, Becky Seifried from the University of Massachusetts Amhurst and Justin Colson from the University of London Institute of Historical Research. I think Becky's going to speak first. Before I hand over, I'll just very quickly want to say hi to everybody watching live. If you're watching live, please do use the live chat feature, which is either to the right or underneath your video on YouTube. Just to say hi, use the chat, let us know where you are and that you're watching us live. It's always good to know who's around. But also if you have any comments or questions throughout the session, please feel free to put them in the chat there, and we'll try and address them later in the session. For those of you who are not following this via SunoikisisDC Digital Classics but have found this on YouTube, there's a link beneath the video back to the SunoikisisDC session page, which has suggested readings and an exercise that you can follow for this session, which we strongly recommend as part of what's coming out of this session. For anybody who's not watching this live, who's watching this later, this video remains on YouTube. Welcome also. Unfortunately, we won't get live chat from you, but I think if you want to get in touch with any of us, if you have any further questions or you're interested in using this in either learning or in teaching, I think we'd be happy to hear that you're doing so. So do feel free to get in touch. Okay, I think that's it for the preliminaries. I'll hand over now, I think, to Becca Seifried to get us started.
Hi, everybody. I'm so glad to be here and take part in this session again this year. Just for introductions to continue that, I'm the Geospatial Information Systems librarian at the University of Massachusetts Amhurst. And we're going to talk today. We're going to start with how GIS data works. We're going to cover the concept of coordinate systems. I'll hand it over to Justin to talk about vectors and rasters and symbology. And then each of us will give a demo to show you how to use GIS software, desktop software that you would install on your computer to do some spatial querying and georeferencing. So to start, core concepts of GIS. How does GIS data work? One way to think about GIS is to conceptualize it as layers that are stacked on top of each other like a cake. So GIS data are, one thing I like to always remember, they are essentially an abstraction of the real world. So in this schematic drawing, we see here, the real world, and we are representing different aspects of the real world as individual layers in the GIS cake. So we might have at the very top a point layer that represents customers in the real world, and then a line layer representing streets, and a polygon layer representing plots of land that are owned, parcels. Then we have two raster layers, and we'll talk about what that word means in a second, that are representing first elevation and also land usage. Anything you can imagine in the real world that you might want to represent in the GIS, you can. So we can represent, as we'll see later, amphitheaters as a series of points, or Roman roads as a series of lines. Another concept about this GIS as a layer cake is that layers at the top of the stack are always rendered above lower layers, which means anything that's below another layer, you won't either see it or it will be seen through the top layers. Another way we can think about GIS is as a database. So most GIS data that we're going to see today has two components. One is some kind of location in space, and this is usually represented as an XY coordinate pair of some kind, showing where it is on the Earth's surface. And then GIS data also has some kind of additional data that goes with it. And that can be as extensive as a table that has all kinds of attribute information like ID, name, the size, the date, anything you could imagine. Or it might have a value, some kind of measure value like an elevation or a color corresponding to a color that our computer screen is showing us. So a little snapshot, which Justin will talk more about, vector data versus raster data. This is how vector data looks in the QGIS window. And QGIS is the free and open source desktop software we're using today. So we see a series of points here. These are actually from an archaeological survey on Cyprus. The data, I think, are available on Open Context. I believe that's where I found it. And so these are points where archaeologists collected ceramics and other materials while they were doing a surface survey. And so we see, first of all, that these points have an XY coordinate location. Each point has one. And then each point also has a row in its attribute table, which we see in the top right corner. And that has all the kind of information that the archaeologists recorded. So we see a unit ID, we see a latitude and longitude location, quantity of, I assume that's sherds that they collected, and then some other things that they collected. This is what raster data looks like in QGIS. This is actually a snapshot of the Grand Canyon in the United States. So what we're seeing here is an elevation data set. We can't quite see quite as clearly, but GIS is representing this raster as a coordinate location starting in its bottom left corner and building out this grid of pixels, which you can kind of see in the top right corner. And each pixel contains that value data. So again, we have this GIS data set represented as a coordinate location and also some kind of value that the GIS is displaying for us. So I'm now going to talk about some very important concept of GIS that is admittedly hard to wrap our minds around sometimes, but it's so important because in my experience helping people learn GIS, 90% of problems come back to coordinate reference systems. So I like to introduce this by asking this question. If I told you it was 40 degrees today, what would you imagine? I am based in the United States where 40 degrees is something we would use in the Fahrenheit system, and I would be imagining a little snowman or snow person, very cold. But if you're based anywhere else in the world that uses Celsius, 40 degrees means very hot. This is the same concept applied to coordinate systems. I can give you the same coordinate pair, an X and Y location with a number, and depending on the system you're using, it can mean completely different places on the surface of the Earth. So another core concept about coordinate reference systems, or I should say the first core concept, is that of a datum. If you've used this word before, it might have been in some kind of mapping context. A datum is essentially a starting point for your grid. So this is an example from my home, where I live right now, my hometown, Greenfield, Massachusetts, where there are these geodetic markers on tops of mountains. And in different countries, they use different systems. I know in Greece, they use kind of cement pillars, but these were basically the remnants of, the last century of work of really scientific, highly accurate mapping, where the geographers were establishing this grid so they could measure accurately locations off of these known points. So this is basically part of a datum system. There isn't just one datum. There are global datums that are meant to kind of maximize the accuracy of when we're measuring across the whole world. And then there are datums very specific to locations such as countries. So Greece, for example, has its own kind of, datum system, coordinate system that it uses because it's trying to maximize accuracy just in Greece. All right, the next core concept behind coordinate reference systems is that there are two families of them. Geographic coordinate reference systems represent location using latitude and longitude values. So anytime you're trying to measure a location on a three-dimensional surface, such as a globe that's sitting on your office desk, you would measure it with this kind of notation. So the location for where my university is based is 42.3732 degrees north of the equator and 72.5199 degrees west of the equator. These are really common ways to represent location on the Earth. I think by default, if you go to Bing or Google Maps and you right-click and get the coordinate, it's often represented this way with degrees, minutes, seconds, or decimal degrees. If you have a GPS device that you're using out in the field, it will often return your location in this system just by default, unless you change it. Projected coordinate systems are the second kind of coordinate reference system. And the reason why we have them is that it's not super easy to measure distance using degrees as a unit of measurement. If I told you that to go from my library to, the classics department is 0.00001 degrees away, it's going to be hard for you to understand what that means. But if we can flatten that system into a flat surface, I can then give you those units in meters or in feet or in some other kind of measurement that makes sense to the human brain. So this is the main reason why we use projected coordinate systems. However, there are endless and countless ways to take a spherical object like the globe and flatten it out into a flat surface. And so we aren't going to go over all the thousands of ways you can do this, but it is good to know that there are thousands of ways. So there are, in fact, thousands of coordinate systems you could pick from, depending on what you're trying to accomplish. So the same location that I told you before, where my university is based in Massachusetts, can be represented in this system. 704,000 meters in the x-axis and 4.6 million meters in the y-axis. What that means is that the datum, or the starting point, is somewhere really far south and west of where we are. And this particular system I'm using is called WGS 84 UTM Zone 18 North. So one thing to know is that these coordinates can go back and forth. And in GIS software, we have the capability of switching how our map is displayed. That's one of the benefits of using GIS software, is it's very smoothly and seamlessly transitioning between different coordinate systems for us and doing that hard math so we don't have to. The last thing I want to talk about is that any kind of projection necessarily implies distortion. And I recommend Googling the Leventhal Map and Education Center's digital exhibition, Bending Lines. This is the Map Center in the Boston Public Library. They have a really cool exhibit that talks all about how distortion happens when you use a projected coordinate system. So here's an example from a 1954 publication. Somebody drew a face on a round ball and then imagined what it would look like if you used different projected coordinate systems to display that on a two-dimensional surface. So the one with the label A is probably one of the more common projections. If you have ever seen a wall map of the world, it's often in this Mercator projection. And so you can see what it does to the poles is it makes them extend infinitely, basically, which we know that is the reason why Greenland, for example, is often so much bigger on our maps than it really is. So another cool tool you can use to explore this is the truesize.com. I hope that is still an active website. So in the left here, we see the Mercator representation of Alaska and Brazil. But the true size lets you drag one country's shape onto another. And we can see that if we drag Alaska onto Brazil, it's actually much smaller than Brazil. And so that is the power of distortion when we use projected coordinate systems. One last just kind of like sneak peek is that there are many different kinds of projection systems, and UTM is perhaps the most common. It stands for Universal Transverse Mercator. Essentially just divides the whole globe into 60 zones. And then when you're choosing which coordinate system to use for your project, you'll want to choose the zone that corresponds to your area. So where I am in Massachusetts, we span zones 18 and 19. But for example, Istanbul is in zone 35. And you can use different datums with this UTM system. So we can use WGS 84 datum, which is a global datum, or we can use ED50, which is a European datum. Endless combinations. So just as a quick summary, you can refer back to this slide if you want. When would you use one or the other? You'd use a geographic coordinate system if you want measurement units in degrees, if you're globally mapping and maybe general mapping applications. But you would use a projected coordinate reference system if you need accuracy and the ability to measure things in units like meters and feet. Maybe you're working in a specific country or region. And so if you decided to start working for a survey organization or do some topographic mapping, you would probably use a projected coordinate system. For the purposes of today, we're probably going to stick with geographic coordinate systems. But I wanted everybody to know these concepts so that if you do continue playing around with GIS and you run into some problems like your data isn't displaying in the right place, this could be the reason why. All right, I'm going to turn it over to Justin.
Thanks so much, Becky. Gabby, do you want to switch over so I'm, yeah, is this my screen share now? Excellent, thanks. Cool, so just as introduction here, I feel a little bit of a fraud in this session. I'm a historian, I'm a medieval historian, working in the Institute of Historical Research, one of the sister institutes of the Institute of Classical Studies. And I've been using GIS in several different forms as part of my kind of social and economic research for a good few years now. I've been teaching courses that introduce GIS to people coming from a humanities background, and I can only concur with Becky's comment that 90% of the problems that people face are down to projection. That is very much true. But I'm going to just give you some introduction now to kind of two of the two key data types that we're going to be dealing with. And I'm going to be perhaps putting a bit of emphasis on the way that as humanities scholars, and especially those interested in the past, whether that be the modern, the medieval, or the ancient past, we're often dealing with things a little bit differently to people working in the present. And assumptions that you might find in general courses in GIS might not be quite so applicable to us thinking about the past. So the first and perhaps intrinsically simpler form of GIS data type that Becky mentioned is a raster. A raster is a technical computing term for an image, a static image, an image formed of pixels, just like you would get from a phone, from a camera, from a scanner. That means that it's very simple to work with. In some respects, it looks right straight away. The world is represented intuitively in the way that either the satellite, the aerial photography, or perhaps the historic map in an archive that you're working with represents it. It's there on your screen, just the same way it was originally. And that's simply a pixel by pixel grid representation of different colors, different RGB colors or different grayscale colors. Now, that also has significant disadvantages. It means that the computer and the GIS system don't actually know anything about what those values represent. You can intuitively look at the image, and the example here taken from Esri's manuals shows the top-down view of the real world rendered as pixels. You can look at it and intuitively figure out that the blue probably represents water, the red kind of regular shaped objects probably represent houses or buildings, and the orange represents a long narrow thing, perhaps it's a road. Intuitively, we can work that out. The system doesn't know any of those things. It simply knows that they're pixels of those given colors. So there are many disadvantages to working with rasters, but a lot of the time rasters are what are most commonly and easily available to us, especially when we're trying to work on the past, on the physical environment. So scanned historical maps are some of the most common things that the people that I tend to teach are trying to work with. Maps from archives representing maybe the 17th, the 18th centuries are very common subjects that people want to use in GIS. And we're going to be using a similar example in our tutorial today, representing the classical world, but drawn in that period. So in order to use those pixels in a raster in your GIS project, as Becky said, you need to give it at least some degree of coordinates. And as Becky said, that's usually the bottom left, the bottom west corner of an image will be its starting point where it's going to be rendered onto the map. And that's what's known as a spatial reference. It's the reference point where this image, where these pixels are going to be rendered. But things don't often work quite as neatly as simply defining the corner coordinates of an image. You might find that the image you're trying to work with is perhaps an aerial photography, which is subject to parallax error, which means it's sort of distorted from the angle that it's been taken at. It might be a map drawn in the past, which was surveyed less accurately than we might need to use today in order to join it on and layer it with, for example, OpenStreetMap or other base maps. Or it might be a case that it was drawn in a projection that either was different to the one that we need to work with, or quite often the case you'll find with historical maps is actually unknown which projection it was drawn with. So not only do we need to go through a process of assigning spatial references to the corners, we need to assign spatial references to much more of an image to make it possible for it to be usually warped onto the coordinates of the rest of your GIS project. And that's a process known as georeferencing. And the example you can see on the screen here is one of our favorite maps of London in the 17th century. This is Morgan's map of 1682 of London. And you can see it's got ugly black borders at the top and the bottom in quite irregular shapes. The original of this map is perfectly square. This is the result of the georeferencing project being applied to this map, where I think it was actually something like 10,000 points on the surface of this map were referenced to the real world geography today. Process of matching recognizable features between the source and the destination maps, as we'll play around with later on, to make sure everything is in its correct spatial reference point. The result, therefore, is warping. So this is a geo-rectified version of the map. And the process, as in fact Becky already showed you in one screenshot, looks a lot like this. You have two windows, and you are literally going through a manual process most of the time of choosing a source point and choosing a destination point. Coordinates on one image, coordinates on the other image, and tying them together, and then applying an algorithm to do the stretching. So that's how we would deal with archival rasters, archival maps. The other key way that we might deal with rasters or need to use rasters in a cultural heritage GIS project is usually where it comes to elevation. And the format and the title that you'll see most often is LiDAR. LiDAR is like radar, but with a laser. It's a way of capturing elevation details, usually from aircraft or from satellites. And it's data that is usually available from pretty much every national mapping agency in the UK. It's available from the Environment Agency. Has particular relevance to, for example, working with flood risk. But it's supplied as a raster because it's a continuous picture of the landscape, and it represents the elevation data not as the kind of tabular data that Becky's example of that archaeological work of the number of finds in a given area, rather than representing elevation as a height in numerical terms. It's representing elevation with a pixel value in terms of its color along a scale from white to black. There are two types of LiDAR imagery that you might often work with. And usually most data sources that provide these give you the choice. The same supplier, the same mapping project, mapping agency will make these both available. There's a digital surface model, which represents the complete surface as reflected back to the laser on the capturing device, complete with everything that laser beam hits, including tree canopy, buildings, everything on top of the surface of the Earth literally being reflected back up to the aircraft. But there's also usually what's called a digital terrain model, and that involves filtering out a lot of the complexity that's added by things like trees and buildings. It will still include earthworks. So quite often historians are frustrated that they get what they think is going to be a beautiful kind of landscape history source, and actually the relatively recent new highway is still clearly visible because it's got major earthworks all around it, cutting through their ancient landscape that they want to depict. As you can see in the image here, though, it's very ugly. It's not a representation of the world that you would necessarily recognize in particularly clear terms. There's ways we can play around with that. We can change the way the color scale is represented. But fundamentally, this is pixel values which aren't there to represent things to your eye visually. They're pixel values that are there to represent values of elevation on a continuous scale on a continuous map in all directions. So we can apply algorithms that will make this a lot easier to see. And we generally talk about this as a hillshade. This is a transformation that lets you see the results of the elevation that's being mapped in a familiar and intuitive way, rather than literally being the value, the height value represented as a color on the scale of gray to black. It's representing the visual effects of shadow. And this is exactly the same area. I'm sure no one recognizes it. This is Ipswich in Suffolk. It works for that. But as historians, we might have a lot more interest in combining this with other map features. And as Becky said, things are literally layered together in a GIS. So here's a historic map of Ipswich from the 1930s, layered above the hillshade map taken from the LiDAR. And we can see the power of adding those. We've added a third dimension visually to this historic map. Vectors, though, give us a lot more analytical potential. We saw in Becky's example the fact that there might be a value attached to each of those observation points. Those observation points can take any form. Vector data simply represents the world purely by coordinates. There's no pixel values, there's no overarching image, there's just lots of coordinates. Those coordinates can be a simple pair of coordinates which makes a point. It can be a series of coordinates building a line, or enough coordinates to build up into a closed shape known as a polygon. But the real power comes from the fact that it is a database. This is a table of those coordinates, exactly as we saw in Becky's slide, which can have as many other columns in the table as you want, so everything can have properties. And the real power of this is that it means things can be displayed dynamically. You can make the appearance of your map react to and reflect those properties, as well as react to things like zoom level as you move through the map or animate things through time. So when you work with vector data, you can engage in what's called symbology by reflecting those values. You're creating a representation symbology as you work through. use the values in the table to display the map in the way that you want. So here's just a few examples from my work. This is a map of population figures for London's parishes in the 16th century. And it's clearly what's called a choropleth map, a map showing density or showing intensity of figures by color. The darker the color, the higher the population. If you take a look a little bit more closely at the map, you'll see that some of the darkest colors are in fact some of the smaller numbers in the labels here. And that's because this is a map that's taking advantage of the intrinsic properties of a vector shape, of a polygon shape, in that because it's defined by coordinates which are on the globe, which, as Becky said, can be calculated as a projected coordinate system with distances in meters. Every shape has its intrinsic properties like area, perimeter, width, height, etc. So this is actually a map of population density rather than simple population. So I've enriched the historical data that I have purely using the intrinsic qualities of the GIS mapping. And once we get further along with this, we can apply some much more sophisticated symbology methods. These values were what are called summary values. There is a total population for each parish. It's a simple one-to-one match. But we might have a situation, and we often will have a situation, where we have many, many individual data points. In the example here, you can see that there are these sort of petri dish of concentric circles. These are in fact people all mapped to the same towns, the same places on the map. And the info box, which is open on the screen there, has got a list of all the names of all the people being represented, but they've only been mapped to the level of detail of town. But we can play with symbology to represent that overlapping density of things in lots of different ways. So these are QGIS styles known as point density and actually heat map as well on the left-hand side there. So you can create these kind of effects in a dynamic way, in a way that we can, for example, query. We can query dates, times, attributes of these people, and these display styles will update as we go along. The heat map will redraw as we query the data. So there's real analytical power to working with vectors and to playing with symbology styles with it. And I'm going to hand over now to Becky to talk us through an example of that.
Thanks so much, Justin. That was so cool. I don't think I've ever seen that, what you call the Petri dish symbology. I'm going to explore that. Yeah, cool. All right. Goes to show you keep learning things about GIS no matter how long you use it. I'm actually going to go to my slides right now. Gabby, great. Thank you so much. So now we've kind of covered several core concepts about GIS quite quickly. There's a lot to learn. That's why we make this recording available, I think, so you can rewatch it. But now we're going to turn over to demos so that we can show you a little bit about how you might actually use GIS software to accomplish some of the things we've talked about. So I'm going to show some vector-based work using with vector data. And before I start that, I want to explain a little bit about the notion of spatial querying. So one of the readings that's pinned as a required reading in the wiki is Lee and colleagues from 2022. The paper is The Potential Impact of Rising Sea Levels on China's Coastal Cultural Heritage, a GIS Risk Assessment. Too long, didn't read. They basically mapped all of the locations of archaeological sites in a GIS as vector points, and then used an elevation data set and predicted if the sea level rises 1 meter, what sites fall within that 1 meter sea level rise area. And they did it again for between 1 and 2 meters and also 2 to 5 meters. And so this is a figure taken from their publication where we see everything, you know, the things that are in blue are at risk if the sea level rises between 2 and 5 meters, and so on. So this is taking advantage of one of the great things about GIS is that data can be layered, and then we can ask it to identify or select features that are overlaying other features. And there are many different kinds of spatial relationships. I'm going to talk about just a couple of them. These are the more common ones that you might encounter, but there are more. So if you're curious, you can look up GIS and like overlay operations or spatial query relationships. So a very common relationship is intersect. It's the most basic, it's the most all-encompassing. The idea is that one feature touches in some way another feature. And it doesn't matter how they touch or overlay, just that they do. And so these are some examples. That the source is in the upper right corner. It's a little obscured by the SteamYard logo, but hopefully you can navigate to it. So this chart shows us that if we're comparing 2 point data sets, for them to intersect, they have to be exactly on top of each other, which is rare with points. That means you're getting down to the very specific XY coordinate pair. The bottom right corner, we see the more general kind, which is a polygon intersecting with a polygon. They just have to overlap in some way for that to be considered an intersection. And then we have all of the different ways that point slides and polygons might compare with each other. It's very broad. And that is, perhaps, Lee and colleagues could have used intersect to accomplish their map. There's also 2 other more restrictive kinds of relationships, which are the opposite of each other: contains and within. So contains means that one object A entirely encompasses another object B. And so we see, again, let's look at that bottom right corner of a polygon and a polygon. It will only select if a larger polygon entirely contains another smaller polygon. And the opposite is within. Polygon A is entirely within another polygon B. So if one polygon is a little bit outside polygon B, it won't select that. So these are some examples of different ways we can ask GIS to do spatial querying. And there's more than that also. You can do within a distance of, or share a border with, etc. But this is really where we start to see the power of GIS and mapping, as we can do these kinds of spatial comparisons. So I'm going to now switch over to my screen, but before I do, I want to point out I have this reference slide here. If you've never used QGIS before, it's good to just be aware of the way it's laid out. And so I've got the different components of the screen labeled here. And now I'm going to switch over to my other screen. Thank you, Gabby. All right. So this is showing you the wiki page. What I'm about to demo now is at the bottom of our wiki page for today's session, there's a section on exercises. So I'm going to go over a little bit about how to set up your QGIS session. And this is where you would get the link to download and install QGIS. Justin will do the georeferencing in a moment. I'm going to jump down to exercise option B, using spatial queries to find Roman amphitheaters. I'll give you more background, but then end with this exercise so that if you want some help accomplishing this exercise, it should be covered in the video. Okay, so to start, when you launch QGIS, the first thing you'll want to do is start a new map project. And oftentimes when it launches, there's some info boxes here. There's usually an option to start a new session. You can also go to Project New. That's a good way to start a new session. One of the recommendations I always tell people when working with QGIS is to install a plugin called Quick Map Services. One of the great things about QGIS, one, it works on any kind of computer. So if you have a Windows machine or a Linux machine or a Mac, it should work. The other great thing is it's a really lightweight software that has some core functionality, but it can be greatly extended by using plugins. And basically, these are just tools that people have out in the world developed on their own and made available for QGIS users to take advantage of. So we add plugins from the plugins menu. This is also a good time maybe to point out that I'm working on a Mac. So if you're working on a different kind of computer, the screens might look slightly different, but hopefully not too different. So again, to install a plugin, we'll go to the Manage and Install Plugins menu. And I will start searching. I'm going to select all so I can see all of the plugins, and I'm going to start looking for Quick Map services. You'll select a plugin from the menu. You can read about it. And in the bottom right corner, if you haven't installed it before, there will be a button to install plugin. You can see I've already installed it, so it's asking me if I want to reinstall. And then just make sure it's checked so that it's turned on. Once the plugin is installed, you can access Quick Map services from the web menu, Quick Map Services. And this is where we can add a base map. This is the coolest thing about QGIS, or GIS in general, is that we can see where we're working in space with base maps. So I'm going to load the OpenStreetMap standard, or OSM standard map. Once I do that, I now have a base map. So I can see more clearly that this center part of my window is the map area. And in the left, I have a layers menu. I'm actually going to close the processing toolbox because we don't need that today. And now I can zoom in and start getting ready to display my GIS data. So in order to add a GIS dataset, so in the wiki, there is a link to download an example data pack so that you can follow along. I'm going to show you how to load, for example, the Roman amphitheater. So when you download that data pack and unzip it, it should be called SunoikisisDC 2024 GIS pack. There are 2 files in here. Now, we didn't really talk about data formats today. So very quickly, I'll just explain that whenever you see multiple files like this that all have the same file name, but different file extensions, one of which ends in SHP, these together make up a shapefile. A shapefile is a really common data format for vector data. It isn't the only kind. You might also see a file called GeoJSON or a file like KML or KMZ. But shapefiles are really common. And a really important thing to keep in mind is that all of these files need to be together in the same folder with the same file name for GIS to recognize this as a shapefile. One way I can load this file into my QGIS session is to select the file that ends in .shp and then drag and drop it into my map session. You may get a warning. It's very common. QGIS is just letting us know that the base map and the data set we're adding have different coordinate systems. It's asking if I want to change the way it does its behind the scenes magic, and I don't want to change that. So I'm going to click OK. And now I can see a bunch of points have been added to my map. We talked a little bit about coordinate systems. We also talked about symbology. I'm going to show you quickly how to change both of those things. So first, let's look at symbology. If I right-click a data set in the Layers panel and open the Properties window, there are a lot of different places for me to do fun things to this layer, and I'm looking right now for symbology. Clicking on that, I can easily select a different style that's kind of preloaded in QGIS, or I can manually change them. So let's say I just want to change the size and color of these points. I will select Simple Marker, and then I will, under Fill Color, click the drop down to select a different color. So I'm going to go with bright green right now. And then I can click Apply, and it will automatically apply that change. I can also change the size. So I'm going to increase it from 2 to, like, say, let's 6 right now, and click Apply. So that is a really quick way I can change the symbology of the vector data set. You can do this for lines and polygons too. Another fun thing is this layer rendering section at the bottom of the symbology window. If I expand that, it lets me do some fun things. I can change the opacity of my layer if I want it to be a little see-through. I can also turn on effects. So I'll click Draw Effects and then click the little star button. And this lets me do things like, say, drop shadow. I'm going to turn on drop shadow and click Apply. So these are fun to experiment with, all the different ways you might want to change the way your data is displayed. Another thing we talked about was coordinate systems. So I'm going to show you very quickly where you would change coordinate systems and find out more information about them. The first concept is that every data set that is properly georeferenced has its own coordinate system. And I can find out what it is by right-clicking and opening Properties, where we were before when we were looking for symbology, and going to the Information tab. And this tells me everything about this data set, where it's stored on my hard drive. I can see that it's a shapefile format. And importantly, under Coordinate Reference System, I can see that this particular data set is in a coordinate system called ETRS-89, that's the datum, Lambert, extended Lambert Azimuthal Equal Area, or LAEA Europe. So when I made this data set for you, I created the data set in this projection because this is a really good coordinate system for mapping things across Europe and slightly into Eurasia. That's why I chose that after doing some research. The other place I can look at coordinate reference system information is in the bottom right corner of QGIS. This is showing me what the coordinate system of the map is. So I cannot change the coordinate system of the GIS data. It is what it is. It's encoded into the file type. But I can change the way QGIS is displaying it. So if I click that button, I have the option to change that coordinate system and have it display my data magically in a different system or in the same system. So right now I can see that my map is set to a system called WGS84 Pseudo-Mercator. I can filter, I can search in here for LAEA Europe. I can select it because it's something I recently used, so it's populating in here. Or I can use the code, the EPSG code, which I happen to know is 3035 for the one I'm looking for, and then select it from this filtered section down here. And now when I click apply, it changes, you can see the way, it changes the way my base map is now being displayed, because now my base map matches what my points are. Okay. The last core concept, just to introduce you to the GIS interface, is to find out where that attribute data lives. So if I right-click any vector data set, I can open its attribute table. And this is the way I can find out what attribute data is stored with each individual point. So for example, if I select in the table by clicking on the little one in the left-hand side, Dura Europus, I can see in the map, it's selected Dura Europus in the map. And I can also pan across and see all the different information that is stored in here. So in this amphitheater data set, for example, I can see it's got different stuff about area, the elevation at which the site is located, its latitude and longitude. And on the left side, we see just name, label, that kind of stuff. Okay. I could continue talking about how to do things like label and change the size of the dots based on the size of the attribute table, but I want to move on to the notion of spatial querying because it's a common thing that you might want. You might have a large data set like this, but only want to work with some of the data. So I'm going to show you first how to do a select by location based on another layer. And this is not something you would do for the exercise. This is just an additional thing. So I'm going to load in very quickly country layer. So we are looking at the countries, and I'm going to turn off the base map for a second. And again, I could change the way these look, but let's imagine I am working in France and I only want to work with the amphitheaters, the Roman amphitheaters that are in modern day France. What I can do is turn on the selection tool. It's this little yellow rectangle with an arrow. Highlight the countries layer, whatever layer I want to select from, and then click on that country. So right now I have selected France. I now want to do one of those overlay operations. I want to select just the amphitheaters that fall within modern day France. So there is a tool we can use called Select by Location. It's a little yellow box with a small location pin. And if I click that, I'm going to fill out this little box by saying, I want to select features from my Roman amphitheaters where the features are within. So that was one of the relationships we talked about before, are within my countries layer. But the magic happens when I click selected features only. So once I click run, what this tool should do is it will select all of the amphitheaters that are within my selected country. When I click run, we can see indeed it has selected just the amphitheaters that are in modern day France. If I open the attribute table of my Roman amphitheaters and filter, so I'm just seeing the selected features, I can see that I have selected a total of 36 out of 272. From here, I could export my selected features. So if I right click and go to export, save selected features as, this will give me a chance to save just that section that I selected. So I would navigate to a location on my hard drive by clicking the Browse button, find where I want to save that and give it a name. I'm going to make sure that the format is Esri shapefile, just because I want to keep working in that format. And then I can click OK. And what we see if I turn everything else off is that it has now successfully exported just a component. I don't know what just happened to my screen. Hopefully you can hear me. You're going to use these same techniques if you decide to do the exercise B, which I will very quickly show you. So we have our core amphitheaters data set. I'm going to deselect by clicking that button. And we're also going to load in our roads, which is part of that GIS pack. So Roman roads.shape. There we have them. So we have our Roman amphitheaters and we have our Roman roads. Oh, I'm going to reorder to make sure my amphitheaters are on top of the roads. And now the hypothesis that I give you is, or the question I want to ask is, what amphitheaters in this data set were within, let's say, 500 meters of a Roman road? You could come up with another question you want to ask, but that's the one I'm going to do. So very quickly, these instructions are in the wiki. We'll go to Vector, Geoprocessing Tools, and click Buffer. And we're going to create a buffer around Roman roads that is 500 meters on either side. And I'm going to leave everything else default. QGIS is going to save this as a temporary layer, which is just fine for me right now. You could also save it to your hard drive if you wanted to. And if I click run and close, we can see what it's done is it's created these little buffer polygons around the Roman roads. Try to make the Roman roads a little bit easier to see. Okay, so we can see that we've got these 500-meter buffers around the roads. Next, we're going to select by location. So that's that same tool we used to select amphitheaters within France. So select by location. I'm selecting from buffers where the features intersect roads. I might have done this the wrong way. I think I was supposed to buffer the points. Let me check the wiki really fast. Yep, we were supposed to buffer around the amphitheaters. This is why we write down instructions. Let me do that again. So geoprocessing, buffer, we're going to input the amphitheaters, Roman amphitheaters, 500 meters around the amphitheaters, and then click run. Let's confirm that happened. Now we see we have 500-meter buffers around my amphitheaters. That is what I wanted to do. I'm going to remove the accidental buffer. All right, now we can do our spatial location search from buffers that intersect the Roman roads. So again, we're selecting any 500-meter polygons around our amphitheaters that intersect, which means touch in some way a Roman road. Then I'm going to click run. And we can see, for example, this one was selected. It's in red on my screen, which is what we would expect because I can see that there is a Roman road going through it. What are some? This one, for example, which is not near a Roman road, was not selected. It is still pink in my screen. Next, we can select from amphitheaters features that are within the selected buffers. So again, I'll do my spatial selection, select from Roman amphitheaters, where features are within, uncheck intersect, the buffers. So I'm going to click buffered, but again, doing that magic like we did with the France example, we want to select features only. So right now it should select the Roman amphitheaters that are within the polygons I've currently selected. And the polygons I currently selected are all of the buffers that intersect a Roman road. So now when I click run and I zoom out, we can see very clearly all of the selected amphitheaters that are in red that are within 500 meters of a Roman road. All right, I have ended my demo and I'll turn it over to Justin.
You're still muted, Justin.
Someone has to make that mistake, don't they? Every time. It was my turn today.
GIS is all about making mistakes and then immediately figuring out what the mistake was.
We're talking about how risky it would be to do a live demo, weren't we? So, yeah. So I'll run through these slides first, which you've now seen in reverse order. So just a few slides to talk through the kind of theory and considerations that you need to apply to doing a georeferencing project. But we'll look at a related example taking in a archive map, what is it, 18th or 19th century? Looks kind of 18th century to me, map of Rome into a GIS project, and perhaps think about how we might then use that to digitize features from it. I think actually working with legacy archaeology data, what people might call grey data from archaeology, is actually quite a common use case for this kind of thing, trying to find previous research that you might harness in a new way within GIS. So there are a lot of sources of pre-existing georeferenced maps. There's also a lot of collections from map libraries and things which will be available to you to download, which haven't been georeferenced. Old Maps Online is probably the best place to start. It's a wonderful service that syndicates many municipal state libraries map collections into a single geo search tool. A large part of it is also the David Rumsey map collection. The David Rumsey's own website is another great place to look. I think the majority of the things are also on Old Maps Online, but there are some things which are perhaps map adjacent or map tangential, which are only on Rumsey's own site. And yeah, a whole collection of other, especially library sites. Obviously, the British Library is out of action at the present time, but some of their best map collections, the King's Topographical Collection, George III's collection of maps, is actually available on Flickr. I don't think they just didn't get around to integrating it with their main collection, and that turned out to be a good thing. So sometimes these things can be ready georeferenced in there to use straight away. Sometimes you're going to need to do the georeferencing yourself. And today we're going to assume you're going to need to do it yourself. So it's actually 19th century, but early. So this is the map we're going to work with, Clark's Plan of Ancient Rome. So it's a reconstruction of the ancient city based on archaeological knowledge as it was early in the 19th century. And it's a particularly nice and interesting map. So our aim is to take this into our GIS project. And to do that, we need to apply the points that we can recognize and locate in our source layer to our target layer. And the example that we've been using so far is OpenStreetMap. It's a very good and comprehensive mapping service, and as we've seen, you can integrate it directly into QGIS using the Quick Map Services plugin. So the task is simply, he says, simply finding points that correspond between the two maps. This is something that can perhaps become more art than science. There are some considerations like how accurate your target layer is. Sometimes we might need to work with a pre-existing historical map, georeference map, as our target layer because there are no common points between the two. Example I showed you of Morgan 1680 map of London actually used a 19th century georeferenced map as its target layer because there are so few common points between the 1680s and the present day. So we can use the 19th century Ordnance Survey as a midpoint, georeference 1, then georeference against that. So your target layer doesn't necessarily have to be a contemporary map. The point is to be able to locate as many common points as you can. And then you go through this process of finding what are called ground control points. It is, as I said, perhaps sometimes more of an art than a science. What are things which are going to be consistent over time? If nothing else, it depends on the period of time that we're talking about. People instinctively often think rivers, but actually rivers do shift their hydrology and do shift their course quite regularly. Their meanders change, they get canalized, they get engineered and messed around with. For the medieval period in the UK, things like churches are often a good reference point. It's going to be different depending on the context that you're looking at. So use your knowledge, use your contextual knowledge to find what is going to be a good point to match against. I'm going to switch now to running through that task. This is the task that's detailed on the wiki page. It's also a version of the instructions that are in the rest of the slides, but I'm not going to run through those right now. And there are slight differences between those two versions. It's probably worth just starting by illustrating the point Becky made about projection here being the one tailored to the area that you're working on. So by zooming right out using Becky's chosen projection here, we can see just how much this is a projection that is biasing, that is privileging the area of interest of Central Europe and the Mediterranean. And you can see, for example, just how much distortion is introduced around Australia and around the Pacific. It's basically unusable. When we discussed this before, I comment that I usually do leave things defaulted to WGS84 pseudo Mercator unless I have a specific reason to do otherwise, not least because that is the Google Maps projection. And it's the projection that's the default in ArcGIS Online and pretty much all other web applications. So when you're developing historical cultural mapping projects, these days you're often imagining a web publication coming out of it. And if that's going to end up being defaulted into WGS84 pseudo Mercator, why not leave it in pseudo Mercator the whole way through is my usual logic. That falls down when it might come to matching things and doing georeferencing at the level of detail in the centimeters rather than the meters. I have hit problems working at that scale with it. But here we are in the QGIS interface, set up just the same way as Becky's, except I'm running in Windows here. And we had the Quick Map Services OSM map here. And we are going to be using the georeferencer tool. Depending on the version of QGIS that you're using, you might find georeferencer under layer and georeferencer or under raster. It sometimes appears. It's also something which is a built-in plugin, which should always be there, but it's not always enabled by default. So if you can't see it, it's not showing up in this list now, right now. But if you can't see it, search for it in the plugins list, and it might be there, but unchecked. So you can go and do it that way to enable it. So we'd go to Layer and Georeferencer. and a complete new window has opened up. And this is an important part of thinking about that kind of source and target paradigm. So we're opening a new window here. We're going to select our image. It's not placed directly onto the map at all, because it's sitting here in a separate window with its separate reference system, which is just its pixel grid so far. So we're going to be going through a task of matching those locations from this map to our base map, to our target map. And this is going to expose, of course, the fact that as a medievalist who specializes in northwestern Europe, I don't know a whole lot about Rome. So I'm perhaps going to struggle with some of this question of finding matching features. And I'm going to probably end up doing things which I've suggested you don't do, like using river points as common reference points. But so let's get stuck in. It's worth observing that in QGIS there is a bit of consistency to the interface in these little overlays in the bottom right corner of a lot of the icons in the toolbars. You've got a consistent orange star for add or create something, a red X for delete, and a blue arrow or blue backed arrow for move something. So what we're doing is building a table, a cross-reference table, a lookup table between these two things. So we select the add point table tool, and then we need to go in and we're going to choose a feature which we think might be consistent. So we can move around, we can zoom in and out using the scroll wheel. At least on a PC, you can hold the scroll wheel and move to pan the view, which can be handy. So for sake of argument, I'm just going to choose this point on the riverbank here. I've clicked and it's come up with a window asking for coordinates. Now, if you were working with a regularly surveyed grid map system, an ordnance survey map, or perhaps an archaeological survey sheet where you have known coordinates, you could just choose the bottom left corner, click once, type the coordinates, and you'd be there. But here we don't have that. So we're going to use the tool at the bottom here from Map Canvas to find a location instead. Now, I'm sure Gabby's probably going to be screaming at me for getting things wrong in the background, but let's say that this is the same point here. I've clicked and now it's returned me back to the other window, and we can click OK, and the table at the bottom starts to build up this cross-referencing of those coordinates. Now, what else can we see here to cross-reference? Is Mausoleum of Hadrian the same as this monument here? Really showing my ignorance. Let's say that it is. Let's choose that. Let's choose that.
Circus Maximus probably hasn't moved in the last 2,000 years.
Where do I find it, Gabby?
Well, so if you find it on your map, it's the thing just there. Yep. And then if you look in roughly the same place on the other map, it's still got the same shape.
Oh, I see. Yeah. The shame. Let's choose. In fact, let's choose the outside. There we go. Any other recommendations that I'm going to be able to locate easily? Let's go here. Which part of it, perhaps? There. There we go. So the slides give you some recommendations on the number of points like this that you should choose for something to work with the different types of transformation that can be applied. The 4 points that I've added here is a basic minimum for most of the algorithms, most of the transformations that are available to us. In general, the more you can add, the better. I've gone into the settings, which we access via the yellow cog symbol there. And this is where we access that selection of transformation types, which are detailed in the slides. The slides do give a nice explanation of the differences between these, but if I generally always describe it as a list of increasing aggressiveness. The linear transformation at the beginning here is the simplest, and the one which will apply the least. Well, it won't really apply any distortion, only apply scaling and rotation to the map, whereas the ones towards the bottom of the list are going to apply the most dramatic warping to make everything fit as closely as possible. Think back to that 17th century London example that I gave. So I usually choose one of polynomial 1 or 2. I haven't chosen that many here. Haven't many points so far, so let's choose a less aggressive one there. We then get the option to set the projection of our output file. As Becky hinted earlier, once you create a GIS file, the projection is kind of baked into it. The coordinate system is baked into it, and it's relatively difficult to then change it. It can be reprojected on the fly as you use it, but once it's defined in the file, it is defined. So choose carefully at this point. So let's leave it as the project one, the ETRS 89 one, and note that it's going to be actually outputting it to a different file. Becky's vector operations were happening earlier with a temporary file. When you work with rasters, the file sizes are often so much bigger that temporary files aren't always possible. So you're going to be saving a new file to your disk. And that's an important kind of difference to bear in mind when you're working with GIS compared to your typical Excel or Word or something like that, that you are often not just changing something that you can press undo for, you're actually, when you do an operation, creating a new file. And you're going to be ending up with, each time you iterate, a new file, and lots of new files potentially. So I'm going to leave that on the default. We've got some more detailed options here we don't necessarily have to change. One that might be very useful though is use 0 for transparency. That will avoid the black border around the edge that results when you do take something out from being square, which you saw in the London example. So we've set those settings. You might have noticed the coordinates and things changed here, reflecting the new projection that's going to be going into. And then we can press the play button. Successful. You might have seen a slight change in the background here. And there we go. We've got a slightly warped map in vaguely the right place. And I'm going to take that as a win for having done this live. But I'm sure you can see now the value of that and the fact that we have now got this added to our layers panel. We can do things, if I drag this back over here, like playing around with transparency. As well as now using this in conjunction with vector layers, or even creating new vector layers to trace features across. So lots of potential, but I'll call it a day at that point.
Fabulous. That's great. Thank you very much. Thank you both very much.
And I must apologize for my ignorance of where to find the Circus Maximus in modern Rome.
I only knew because I saw the shape on the other map. I wouldn't have known otherwise. We had a possibly more useful suggestion if we'd noticed it in the live chat from Elizabeth. But
oh yeah.
Anyway.
all screaming at me. Yeah. Cool, thanks. So, Gabby, what are we moving on to now?
So this is so I think that's it for the regularly programmed scheduled programming. That's what I'm looking for. I guess just if anyone, obviously, if anyone online has any questions, please post them in the chat. We'll look at those. But does anyone have any other? Do either of you have any, anything else to add? Questions for each other or anything like that?
It might be worth adding, if while I've still got the screen share running, that this is very much an iterative process. As I said, it's an art rather than a science, and it's something that you're going to have to potentially do and redo. It's useful to note that there are these little red lines that have now grown out from the points I selected, showing, there's a proper explanation for these in the slides, but showing the amount of distortion that effectively is being applied around each of them. So trying to make those lines as short as possible is the general objective. A useful thing that you can do is save the table of the points that you've built up here. So you've kind of got a safety net of being able to open your file afresh, load the points again, and carry on from where you left off in another session if they haven't necessarily been saved properly automatically. But yeah, be prepared to iterate. It is an art rather than a science. Probably also worth noting that you do occasionally have to georeference vectors, especially with, if you work with architects or archaeologists, you might have to georeference CAD files, .dxf, .dwg type files. The process is a little bit different, but it's the same concept. But yeah, that's it for now.
So we have a question from Elizabeth, which I think, Justin, you and I have probably already had this conversation with her. So Becky wants to have a first shot at this. There is a range of factors that would lead to deciding between ArcGIS or QGIS or indeed other tools.
Yeah, so in my experience, as somebody who works at a United States institution, ArcGIS is incredibly common as a software here, and that is because Esri, which is the company that makes it, really pushes to get students and faculty free access to ArcGIS here. Another contributing factor is that a lot of GIS technicians and offices that employ GIS specialists, such as local governments, the people who are mapping our sewers and our utility lines, they have contracts with Esri to pay for ArcGIS software. So the key difference is the cost. When I did instruction in Europe, I found that students didn't usually have access to ArcGIS. So that is really the experience I had that drove home why QGIS is such a valuable software, because it's free, it's open source, it is very actively developed, and it runs on multiple kinds of computers. So if you're looking for cost-effective and you have a Mac or Linux, QGIS is a much easier program to use. If you have a Windows machine, because ArcGIS only works on Windows, and you have a lot of money, you can purchase ArcGIS. The other factor I would think about is the amount of educational material that exists. Esri is a very large corporation, has invested quite a lot in infrastructure related to education. So sometimes I'll use ArcGIS tutorials, the free ones, tool explanations, even though I'm teaching with QGIS, because they often have more instruction. The third difference I'll point out, I think QGIS's capabilities as a desktop software match where ArcGIS was 5 years ago. It's really great for all the kinds of things we've shown you today. But Esri as a company is now reaching out more into web-based GIS. and mobile apps, and everything is on the cloud, including processing. So there's a much more robust cloud infrastructure. So if that's something that you'll need for your project, looking into a subscription for Esri might make sense.
The other thing that occurs to me is that if we'd been having this conversation 10 years ago, I expect we probably did have this conversation 10 years ago at some point. One of the things to bear in mind, we would have said at the time, is that QGIS is buggy as hell. That sometimes it'll pretty often it'll crash, especially when we're doing the sort of geo-rectification that we just saw. You try it 3 times because it's crashed each time before you actually get it working, and things. That's not so much the case anymore, especially with some of the more common features. So although ArcGIS has also improved a lot over time, QGIS has improved a lot to the point that it's no longer barely usable. It's no longer something you'll only use because it's free and you can't afford something better. It's that's something to note. And the other reason that we use QGIS in the SunoikisIS sessions is that we have a principle. This is a very practical principle. It's not necessarily a philosophical or a religious principle that everything has to be open source, but a very practical principle that this educational resource is used by people worldwide, and we can't assume that that people will have access to resources, that people will necessarily be affiliated to an institution that has these expensive resources, or even an institution at all. So that doesn't mean that you might not choose to use ArcGIS. You might even do the same exercises we've just been doing using ArcGIS as another way of following up on this, which I guess also makes the point that if we're learning GIS, the things we're learning are still true. The menus are in different places, and they might be called slightly different things. But the vast majority of what we're learning would be the same if using ArcGIS or QGIS, or someone name another common GIS tool. I can't.
They're the only two left standing, aren't they? MapInfo has died a death, apart from, it seems, an English local government. But just again, it's a question of lock-in and path dependency and things like that. That's important. The way I always kind of describe it is that the QGIS has been built by people who learned GIS in ArcGIS. So the paradigms are the same, even if there's slightly different names for the tools or slightly different icons for things. And you're totally right that it's improved dramatically in terms of stability. The one thing I would say is a kind of a flip side to the advantage of all the plugins is that sometimes introduces problems when whoever was developing the plugin to do the thing that you need abandons it, or it's broken by another update somewhere else in the system, and whoever developed it hasn't had time to fix it yet, or whatever. And Quick Map Services is a good example of that, in that it's the kind of 3rd or 4th de facto plugin for adding OpenStreetMap base maps that I've used in the 5 or 10 years I've been using QGIS, because they keep coming and going, and I think largely actually over kind of copyright issues. So yeah, plugins can be a problem as well as an advantage without that kind of central coordination. ArcGIS costs, yes, if you're a corporation, are dramatic. But for UK universities, we're talking the single to early double digits thousands per year for an institution, which sounds like a lot to an individual, but in the scale of things isn't a huge amount. And one tip is you might find that your geography department in your university administer the account for it rather than your IT services department. So you might think, oh, my login doesn't work, we don't have an account. Actually talk to your geography department. You might find that they administer the account separately and they might have to enable it individually. They do also have now a private subscription, which I think is about £200 a year in the UK at least, which again might sound like a lot, but if you compare that to Adobe Photoshop, you can easily get to that per month for Adobe Creative Suite. So yeah, it's not as bad as it looks, but the big advantages of using it are the cloud integration, not least that completely effortless ability to publish a web map almost with a single click, even from the desktop to being on the web and available to be shared with anyone within seconds, is really, really powerful, as well as those new features, really powerful 3D. Using that elevation data to view your map in 3D is possible in QGIS, but is really clunky. Just switch your ArcGIS project from map mode to globe mode, and suddenly you've got very intuitive and interactive 3D views. Really great little tools. They've got like drone to map. So if you photogrammetry, I think features in perhaps sometimes in other points in this course, to better chuck your photogrammetry data straight into ArcGIS and have that rendered into the 3D in your GIS project seamlessly. It's quite a killer feature depending on the type of thing that you're working on, especially archaeological sites. That can be a real advantage. And some fun things I've even started to play around with, like the city engine, which plans new cities. You can define the parameters. So what are the characteristics of a Roman city, of medieval city? Play around with modeling what the characteristics are, and that you can make the AI grow you a new city. And that's been, they always use examples of Disney, for example, using that to create the backgrounds of their CGI cities using it. So yeah, not applicable a lot of the time, but a scale of ambition kind of question there is I think, quite a good illustration.
That is very cool, and we're going to be talking about, we'll mention at least procedural modeling in the 3D modeling session in a few weeks' time. So I think if no one currently involved in that session uses QGIS and could show us that, we might ask you if you could 5-minute demo. That would be pretty cool. Thank you. Cool. Any other final comments? I'm aware we've used up the time that you both so generously are giving to this session. And as I say, if you're watching this slightly too late to ask a question live, feel free to drop me a note, and I'll almost certainly pass the question on, as I probably won't know the answer. But yeah, always very happy to chat. Cool. Okay, wonderful. Thank you very much. And let's see you all next week, those of you who are online, where the session is on ethical responsibilities and 3D methods in cultural heritage. Followed 3 weeks later by the 3D modeling session I was talking about. Cool. Thank you all. See you.
Thanks, everybody.
Cool.
Happy mapping.
Cool.